Well, hello everyone, and welcome to today's presentation, Navigating the World of Wi-Fi. Before we get started, I want to go over a couple of just basics in regards to the webcast. Listening to this online event, the audio portion of this webcast is broadcast over the internet. Make sure your computer/device's audio is available, unmuted, and the volume is turned up to an acceptable level. If you're having trouble with receiving the audio, please select the question mark in the upper corner of the TalkPoint interface and select Test My System Now. This will give you information on your connection and how to remedy any problems you may have. When it comes to asking questions, it's easy to submit your question for our presenters during the event. On the left side of your screen, there is a box labeled Ask a Question where you can enter your questions. Questions related to the webcast topic will be held and answered during the Q&A session at the end of the event. Questions related to technical issues can also be entered in this box and will be immediately answered by our webcast producers. Today's agenda, we're going to start off with talking about the evolution of wireless networking standards, the 802.11 standards. We will also talk about the physics of RF for wireless networking, the importance of QAM and what it is, how multiple antennas can be beneficial, how data rates are determined, and I'll finish up with a little bit of why Ruckus Wireless really outperforms its competition. At the very end, we will have time for Q&A, so please ask away. I'd like to make sure we answer any and all questions by the end. My name is Nathan Holmes. I am the technical trainer for Access Networks. I have over 20 years in the custom AV industry. I was with Access Networks' second dealer starting in 2007. I'm a CEDIA certified instructor, also Ruckus Wireless WISE certified, and a member of the CEDIA Tech Council. For those of you unfamiliar with Access Networks, we provide industry-leading, enterprise-grade networking solutions for the modern home. We have custom network design and support, and our certified IT team has backgrounds in both the IT and AV industries. Diving into this, the wireless networking standards really comprise a number of things, and before we can understand how and why they've evolved over the years, we need to start off with some of the parameters that are included within them. We need to talk about frequency and modulation and QAM. What is it? It's a lot more important than people understand and I think believe. That will lead us into an understanding of data rates, and then we can actually talk and see how the standards have evolved over the years. Frequency is the rate at which a carrier wave repeats itself. Most 802.11 protocols use 2.4 and 5 gigahertz frequencies for transmission. There are other frequencies within the standard. You've got 900 meg, you've got 3.7 gig and 60 gig. There's some others out there, but they're not very widely adopted. The most used, especially in residential, are the 2.4 and 5 gig. Although, because we're having so many Internet of Things devices being created, there's a big push to use things like 900 megahertz because they have lower power usage. Modulation. Modulation is the idea of imposing an input signal onto a carrier wave. This input signal can either be analog or digital. Now, analog basically means to make and send more data, we have to use a faster signal. So there becomes a limit to how fast we can make the signal that's running on top of the original wave. So there are limits to analog modulation. When it comes to digital modulation, we want to send as many bits as we can, digital bytes, digital bits of information, within each frame that we send. So there's an idea that we can send more and more bits per. The newer presentation is, the newer technology is digital, or orthogonal frequency divisional multiplexing, which is digital. Did we lose me? I think we might have lost communication. Let's see if we've got somebody here. All right. I think we paused for a second there, guys. I don't know exactly why. It dropped out. Hopefully you can still hear me. So let's dive into the next thing called QAM, Quadrature Amplitude Modulation. QAM is a lot more important than I think most people understand. QAM is the idea of having two carriers with the same frequency being amplitude modulated independently. The phase of the two carriers is 90 degrees shifted from each other, which sounds like a whole bunch of complicated, ideas, but the idea is we get a quadrant scenario or constellation diagram where we can now basically have a pinpoint in space in each of the four quadrants. So we can identify at any point in time 4 different points where we can send data. This is for QAM. So we're essentially sending 4 bits of data at each point in time. And because of the phase shift between the two carriers, we can know exactly where they're at and determine what that data is. To send more information in the same amount of time, we have to send more bits. So we have 16 QAM, which would give us 4 bits per quadrant, or 64 QAM, or the new in 802.11ac standard is 256 QAM. Now, the problem we face is as more and more bits are being sent per quadrant, there's less space between each of these bits. So therefore, the signal has to be a lot cleaner to be able to hit 256 QAM. So when trying to hit the high standards with 802.11ac, it's really important you have a very clean signal, but it has a high signal-to-noise ratio, which we'll dive into a little bit later. Data rates, as in which data rate it's going to choose to communicate with, is the speed at which data is transferred. The maximum theoretical rate is a maximum rate that we can have with each standard. Each standard has defined if in a perfect world and perfect scenario, everything together is one, then it would work together. The actual connection data rate is the negotiated data rate between a client device and an access point. And this is going to be based on the signal-to-noise ratio within the given environment. Higher signal-to-noise ratio will give you higher QAM rate. If you have bad signal-to-noise ratio, you're not going to get high data throughputs. Okay, so now that we've talked about what the bits and pieces of these are, we can kind of start to understand how the standard has evolved. The 802 standards were actually developed in February of 1980, hence 802. It took until 1997, 17 years later, before we had our first ratification of something involving wireless networking, which was the 802.11 standards. The initial standard was at 2.4 gig. It had analog DSSS modulation, a maximum of 1 antenna, and it really could only hit a maximum theoretical data rate of 2 meg, but you achieved 1 meg, which was amazing because we had never had wireless standards before. A couple years later, though, we finally got to see something that actually hit some usable standards. So in '99, we released both 802.11a and b at the same time. 802.11b was much more widely adopted because manufacturers had already been making 2.4 gig boards for a couple of years. So even though it was only a max rate of 11 and realistic rate of 6, it was much more widely adopted than 802.11a because A was 5 gig. So you had to use a whole different set of boards, and it was also digital modulation. So there was a lot of changes that manufacturers had to do to be able to embrace the 802.11a standard. So everything was B, and we were going along, but people wanted faster. So in 2003, 4 years later, we got 802.11g. Now G was able to hit 64 QAM, the same as 802.11a, but it still kept us in the 2.4 gig spectrum. So even though there was a lot of other devices sharing it, it still meant manufacturers could still use the same antennas, same chipsets. So by reaching the 64 QAM, though, we were able to reach a 54 meg theoretical rate and 22 realistic. Still weren't going that fast, but back in that day and time, we didn't really do a lot on the internet. You did pages here, some bulletin boards, some emails. You didn't have a lot of streaming like we do today. Because of all the streaming and the different things we face today, we started seeing new standards. 802.11n came out in 2009. N was the first and only standard that's 2.4 and 5 gig, but it also introduced some new things. Although it stayed at 64 QAM, it introduced multiple antennas and the idea of being able to bond your channels. So you could double the size of the pipe of information you were sending down. This allowed us to hit theoretical rates of up to 600 meg. Realistically, we did see rates of about 350 megahertz, which were substantial over anything we'd had in the past. So it became very widely adopted. However, as with everything, our technology has needed more and more bandwidth as we've got more and more streaming and high-definition video and all these online gaming. So in 2014, 802.11ac was released. This also used digital modulation. It was now up to very high throughput OFDM. And for the first time, we were able to hit 256 QAM. It is 5 gigahertz only. And to be able to handle all this width and needing more speed, the standard was written to have up to a maximum of 8 antennas. And although we probably won't see it used, you can do a maximum channel width of 160 megahertz, which in theoretical world will allow up to a 7 gig data rate. Realistically, you're not going to see that, and it's not very common to see things over about, say, 800 or 900, but it is definitely showing the progression and how much faster things have become because we've needed to be there. So to be able to get to these different standards, we've had to, we have to understand what happened on the physics and how we created this transmission of wireless data. We're going to talk about the physics of Wi-Fi. We're going to talk about why I believe Wi-Fi is southern. We're going to talk about interference, and that will lead us into proper wireless deployment. We'll talk about antenna technology and how antennas can either increase or decrease the amount of signal being sent by an access point or a client device. We're going to talk about a technology called transmit beamforming and why in the past it's really not provided any benefit. And we're going to talk about something that really did provide benefit, MIMO, multiple in, multiple out. To understand the physics of Wi-Fi, we already know that frequency encoding is used on the 2.4 and 5 gig spectrum. Now, higher frequencies can transmit more data more rapidly. However, higher frequencies have a shorter effective range. In fact, when you're designing your installations for 5 gig coverage, you're usually going to have to design for half the coverage area you would for 2.4 so that you have proper density for 5 gig coverage. Wi-Fi is southern is a term that someone told me a couple years back that I think really does help understand how Wi-Fi works. In the South, if one person talks, another person listens. Once the first person finishes, then the second person will respond. It's a very respectful type of communication. Wi-Fi is the same way. When one client is transmitting, all other clients stop. It's considered half duplex. Nobody talks over each other, and it's only a single communication path, so you have to wait for the first person or first communication to complete before you respond. This means that each client listens before transmitting, and each antenna listens to only one device at a time. It's important to understand each access point is only listening and only speaking to one client device at a time. So if you're in a room and you've got multiple devices, think about how many devices have to wait for the one other device to finish communicating. If you've got, say, 20 devices in a room, one device talks, 19 listen. Then the access point responds. Then another device talks, and 19 listen. This means that speed is going to be diminished by the number of devices, and it's half duplex. So not only do you have half the speed of the conversation, but the slowest device on the channel is going to limit the speed. What I mean by that is, if you've got a device that's communicating on 2.4 on 802.11b, it's going to take longer for its transmission than a client that's transmitting on even 2.4 802.11g. So each client will respond and transmit as fast as it's capable, but older protocols are going to transmit slower, and therefore the rest of the devices have to wait while that transmission occurs. When designing networks or wireless coverage, one of the standard formulas is pretty much say what's the maximum data rate of a connected device, divide that by 2, and then divide it by the number of clients. So if you've got 20 devices in a room, and the maximum connection on 802.11n is going to be 300, say, well, divide that in half as 150. Then divide it by 20 clients, and you might be down to 7 meg. You don't have your 7.5 meg. Those are really slow data rates. So you have to be aware of how many devices are going to connect and how many devices are going to be using the wireless simultaneously. Whether or not they're connected is also important because every single device that can see an access point will try to connect to it. Even if it's not allowed to and hasn't authenticated, it's still going to try. So if you have an access point that it can only handle, say, 25 clients, and you've got 300 devices all trying to connect to it at the same time, that access point is not going to be able to perform. And a lot of times, it won't even be able to transmit data for the clients that are connected to it. The entire network will stop functioning because too many devices are trying to authenticate, and the access point just can't handle it. Let's talk about interference. Interference is a disturbance generated by an external source that alters, modifies, or disrupts the desired wireless signals that travels from a transmitting source antenna to a receiving antenna. Basically, how pure or unchanged is the Wi-Fi data that was sent received after it travels through the air? Okay, that makes sense. But we need to think about that Wi-Fi is its own worst enemy. We have something called co-channel interference. Two access points broadcasting on the same channel will interfere with each other. We have adjacent channel interference. Well, channels are not, they're going to overlap each other. And where they overlap, you're going to get interference similar to co-channel interference. Additionally, we have non-Wi-Fi interference from other devices that are broadcasting in the same, unlicensed spectrum as our access point. Plus, you have interference from, the materials in the environment. Co-channel interference is one of the biggest things of interference that you can design out of your system. It will also probably cause you the greatest reduction in throughput. Let's say we have an access point. We know that in the given environment, as you get farther from the access point, the signal gets lower, and therefore your throughput will decrease. So to combat that, we install multiple access points in the same environment. So no matter where we're at, we have high signal strength. However, two access points broadcasting on the same frequency will interfere with each other. Those areas of interference are going to have very low signal-to-noise ratios. Now remember, the signal-to-noise ratio is how much signal transmitted from the access point is received in comparison to how much interference is in the environment. That signal-to-noise ratio value will determine what data rate your device connects at. If you have a high signal-noise ratio, you can connect at high data rates. Low signal noise is going to be low data rates. You have to have high QAM for high throughput. So co-channel interference is one of the easiest things to design out of your system, but can cause some of the most detrimental throughput issues, because you'll still show high connectivity on RF, but you'll have low throughput because there's low signal or noise. Adjacent channel interference is similar in the sense that you're getting radio waves that are interfering with each other. Each channel has a certain width to it. In 2.4 gig, the standard channel width is 20 megahertz. And to be able to choose channels that don't overlap with each other, you need to choose channels 1, 6, and 11. Those are the only 3 channels you can choose where they won't overlap. Now, that's good, but because there's also so many different devices broadcasting in the 2.4 channel spectrum, a lot of times we recommend going to 5 gig because there's less potential for interference. Also, on 5 gig, you start off with 24 non-overlapping channels. Okay, that's great when you're doing, a 20 megahertz channel size. If you go to a 40 megahertz channel size, you drop down to 11. And if you go to 8, you still have 5 different channels where you can choose where you're not going to overlap and not have co-channel or adjacent channel interference. So it's important to understand these premises when designing your systems. One of the harder things to design out is non-Wi-Fi interference, but it is definitely something you're going to face on every installation. 2.4 and 5 gig are open frequencies that are very widely adopted. You've got cordless phones and video cameras. You've got appliances like microwaves. You have Bluetooth devices, wireless music systems. They're all broadcasting in 2.4 and can definitely interfere with the same, your 2.4 Wi-Fi frequencies. In fact, cordless phones, they can give you 100%, reduction of your wireless signal. You won't even be able to connect sometimes. So you have to be very aware of what other devices are going to be in your given environment. Additionally, building materials, concrete, Venetian plaster, steel, mirrors, all of these will inhibit radio waves from being able to travel the distances that they would like to, and therefore will decrease the amount of coverage and throughput you have. When designing for proper wireless deployment, we want to take all of these considerations into all these things into consideration. Channel selection is critical to help minimize both co-channel and adjacent channel interference. Plus, we want to be able to figure out and design around non-Wi-Fi interference. The two diagrams below show how you can utilize either 2.4 or 5 gig frequencies in a way that individual access points are set to specific channels that do not allow them to interfere with each other on either co-channel or adjacent channel. Let's talk about antennas now for a second. All antennas concentrate energy that is transmitted or received. This is an example of an isotropic omnidirectional antenna. In this example, all antenna energy is transmitted in all directions at the same amplitude, same strength. Well, that's great, except for we don't live in a world where that really makes the most sense. Most of the time we have a given space, 8 to 10 foot ceilings, and we want to broadcast throughout that space. So the most common antenna we find in the Wi-Fi networking world is a dipole antenna. A dipole antenna produces a donut-shaped pattern of coverage that has up to a 3 dB of gain within that pattern. Well, that's great. But we also have to understand that it's somewhat directional. So if you point that antenna horizontally, that's going to change that donut to going up and down. So you want to be very aware of that on how, if you have an adjustable antenna on your access point, how moving that antenna or how you mount them is going to affect the environment where you're transmitting it. Additionally, what if we want more gain? We know we got 3 dB from a single antenna. What if we had more antennas? Can we get more gain out of it? Well, yes. We can add more antennas, and that will definitely give us more strength, because it doesn't make sense to add more and more access points past a certain point. One, it's not financially feasible. Two, we already know that they interfere with each other on different frequencies. So there's a limited number that we can install in a given environment. So as we add more antennas, though, something interesting happens. We get constructive and destructive combinations of RF energy. When the signal from one antenna and a second antenna arrive at the same point in space at the same time, you can have twice the signal strength. If they arrive out of phase, you can have no signal. They can cancel each other out. So you have to be very aware of where these are going to arrive in space if you're going to use multiple antennas. This comes into the concept of transmit beamforming. We use phase control to phase shift the antenna patterns so that we can control when they arrive at a certain place in time, and therefore we can maximize use of constructive combinations and even use destructive combinations to cut down on interference seen by devices that we're not communicating with at that time. To see kind of how this works, let's look at an access point. We've got antennas here, and as the signal is transmitted from each antenna, it's phased so we can control how they all interfere with each other over the air. The resulting coverage pattern results in beams where RF signals are added together and notches where they cancel each other out. If we can determine where a client device is in space, well, we can make sure that the beam reaches the client when we're talking to it, and notches hit other clients when we're not talking to them so they see less interference. And depending on which client we're talking to at each point in time, we should be able to shift the phase of each antenna so we can maximize the experience for each client we're talking to. That's great. And it also means if we add more antennas, we can provide additional coverage patterns. This does require a minimum of 2 antennas, and it's an optional standard in 802.11n and 802.11ac. It is chip-based, so it is part of the chipset. When you decide that you want to create an access point that's N or AC, you have the option of turning this on or off. The problem in the industry we have is for this to work, you have to know where the client device is in space, which means your device has to also have transmit beamforming turned on within it so it can respond to the access point and tell the access point where it's located so that it can send its beams to it. The problem is no manufacturers turn them on. So even though it was an existing standard, we don't really see it implemented, and we don't see the gains that it could provide. It does provide some benefit in the sense that it can give better coverage to a given area because it can beamform around different obstacles and walls and things like that, but it doesn't know precisely where a client device is, so it can't truly give all the benefits that it's capable of. It's also mutually exclusive with something called multi-user MIMO, which we're going to talk about next. Before we talk about multi-user MIMO, we have to talk about MIMO. MIMO means multiple in, multiple out. The concept of, let's take, in this example here, the phrase take out the trash. Let's break it into two smaller chunks, take out and the trash, and then send each of those smaller chunks out of individual antennas, being received by multiple antennas on the receiver end. That means we're transmitting smaller packets of data much more rapidly. This is where we've seen the biggest increase of throughput with 802.11n and AC is by utilizing multiple antennas. And as long as your access point has the same number of antennas as your receiving client device, you can see some really high throughputs. Three antenna devices are really, really high throughput devices. But what about if you're just using an iPhone that only has a single antenna? Well, we're not really getting the benefits that we want out of it. And if you remember before, we also talked that an access point can only talk to one client at a time. Well, what if we could change that? 802.11ac Wave 2 brings up this multi-user MIMO. The idea of, if I've got 4 antennas on an access point, well, why can't I talk to 4 single antenna clients at the same time? Well, now you can, as long as the client devices are also capable of 802.11ac Wave 2, and they have that optional standard turned on. For example, a Samsung S7 phone has been Wave 2 capable since it came out. So this means in high-density environments, we've talked about, let's say you've got 20 devices all talking to an access point. Well, if all those client devices were multi-user MIMO capable, then that access point could talk to up to 4 single antenna devices, or 1 two-end antenna device and 2 single antennas. You could really use the combinations however you need to maximize the amount not only of data throughput, but the number of clients that can talk simultaneously to the access point. Now remember, I've said it's mutually exclusive with transmit beamforming. Well, this is because for transmit beamforming, you need to have all of your antennas or multiple antennas talking to a single device. It's got to be able to phase shift to that device. Well, if I've got my antennas talking to 4 different devices, then they can't also talk to that one device at the same time. So just from a physics standing, they're mutually exclusive. All right. We've gone through all of these things, but there's a lot of stuff to digest. So what I wanted to do was show a real-world example of what this really means. So if we take a given environment, the signal-noise ratio of 45 is really high. It's a great signal-noise ratio. So if we were connecting at 802.11n, we'd be at the highest QAM for n, which is 64, the highest channel width of 40. A guard interval is how much space between transmissions there are. A short guard interval is 400 milliseconds. A longer one is 800. So it chooses, in this case, we have the shortest guard interval, so we are reaching our maximum data rate of connection. So we're connecting at 150 megabits per antenna. Well, if we were in that same environment, and we only had a signal-to-noise ratio of 17, which is actually pretty common in our day and age with the amount of interference we have, now we drop down to only 16 QAM, and the channel width of only 20 megahertz, and our guard intervals back up to 800. So at this, we would only be able to connect to a maximum data rate of 39 meg. And depending on how many antennas we're connecting to, you can see that there would be a wide disparity between the negotiated data rates that you're connecting to your access point on. Beyond that, what we have to understand is that your actual throughput when you're connected to an access point will usually only be about 33 to maybe 50% of what the connected rate is. Remember, it's half duplex, so you're automatically going to drop down to 50% of that connected rate. And then with error checking and some things like that, usually about 33% is a good, safe assumption. And that's before you divide by the number of client devices that are connected to that access point. So even though we've got an access point that was capable of 600 meg, you notice on the right side, we're only connecting at 39 and probably only a realistic throughput of maybe 13 meg, which most cell phones can connect LTE at almost 50 meg. So we've got to be aware of this when we're designing an environment. Now, 802.11ac, in comparison, can definitely give us much higher data rates. Okay, we know that if we take the same 45 signal-to-noise ratio and same 17, you notice on the left, wow, 256 QAM, 80 megahertz channel width. Now we're at 433 meg per antenna, but we're still down at 54. We're seeing very little increase going to AC when you've got interference, which means, again, number of antennas, maybe at 867 if you got clean signal, but if we don't have clean signal, then really what are you seeing on an overall throughput? Maybe 5 meg? So it's really important when you're designing your systems that you ensure you have adequate 5 gig coverage so that your client devices are going to be close enough to the access points to truly benefit from the 802.11 AC, 256 QAM and those major throughputs. And additionally, be very aware of using products that can help you understand what additional interferences you have in an area and help ensure that you have high signal and noise ratio for each device, because that's going to be critical for your client experience. That takes us through the physics of standard Wi-Fi and understanding how it all works. I wanted to dive into a little bit of how Ruckus, as a manufacturing company, uses some things that they've patented to provide higher signal and noise ratios for each device, and really this is how they can outperform the competition. Ruckus has some proprietary things. BeamFlex and BeamFlex Plus are the two we're going to go into today. They actually have over 100 patents, but the two big ones that we're going to talk about, BeamFlex and BeamFlex Plus. They also have a zone director wireless controller that ties things together, and by utilizing FlexMaster remote management, you've got full visibility into the wireless network even when you're remote from the project. So, BeamFlex and BeamFlex Plus, they provide higher Wi-Fi signals, stronger Wi-Fi signals at longer ranges, more stable connections at higher data rates, which allow more concurrent users per access point. And remember, it's not just how many people are authenticated, how many people are trying to authenticate. A lot of their access points can have over 500 concurrent clients. So it's even when you're having that party in the backyard where you got 300 people that are they're sitting there with their iPhones in their pocket, and it's all trying to connect, your access point's still going to be humming along. Additionally, they can automatically adapt to environmental changes to ensure high signal noise ratios for each client device. To do this, we need to talk about BeamFlex. BeamFlex is the industry's only multi-antenna approach that can support both spatial multiplexing and constructive signal combination at the same time using only 2 transmit radio change. That's a whole bunch of technical things that probably are confusing, and frankly have been confusing a lot of times to me as I was out in the field. So I worked really hard to kind of come up with a real easy way to understand this. And to do that, we want to look at what a Yagi antenna is. A Yagi antenna uses what they call directors down a shaft. The director is going to reflect certain RF frequencies back at the original reflector so that you can get, again, constructive and destructive combinations. What you end up with is the highest gain antenna, so you can pinpoint RF energy in one direction to either another receiving RF antenna or, in this case, to our client devices. Ruckus achieves this by using multiple adaptive antenna elements that are around a central antenna. They use these adaptive antenna elements, or pattern shapers as they may be. Through software, they turn them on and off. So depending on which client device you're talking to at which point in time, it's going to use different antenna elements so that it can focus all of the RF energy from that access point directly to the client device that it's speaking to at that point in time. This is software-based, and it's an antenna technology, so it's not dependent on the chip-based technologies like other manufacturers that are tied into 802.11n or AC. So this can be used all the way through with 802.11b, G, A, N, AC. All of them can benefit because it's a technology based on how do we make the antennas provide higher gain before we even talk about what we can do with the chipsets. Now, if more client devices with 802.11 AC start being able to use transmit beamforming, guess what? We can add that gain because that's chip-based. And if they're not using it, we can still use this antenna gain with the benefits of MIMO and multi-user MIMO, as each antenna can direct its signal to each client device. In the real world, what this really means is when you take a look at a specific, a static space, let's say this room here, the standard access point on the right, that little blob shows you only the area of the room that's going to benefit from the 802.11 AC data rates, where it can get to 256 QAM. The rest of that room is going to be down in 802.11n, like 54 meg, right around those. BeamFlex, because it can focus the RF energy in that same space, can provide 802.11 AC rates throughout the entire room because it has higher signal and noise ratios. So at a greater distance from the access point, you get much higher throughput. Well, that brings us into another kind of concept, which is polarization of antennas. If you remember back when I was talking about dipole antennas, I said it was very important to know how, when you aim that antenna, it focused that donut-shaped beam of energy. Well, if you're walking around with a mobile device and it's designed to be vertical and you're right in phase with the antenna, great. You can get 100% of that signal strength. Well, what if you're opposed to that? Now you can literally potentially have zero signal strength because you're vertically posed. Ruckus came up with BeamFlex Plus to combat this. By utilizing horizontal and vertical antenna arrays, they can choose which antenna array will be most beneficial to which client device at each point in time that it's speaking to that client. It's referred to as PDMRC, Polarity Diversity Maximal Ratio Combining. It's optimal for mobile client devices because it can, by packet, choose not only where to focus RF energy, but whether to use vertical or horizontal antenna patterns for the highest throughput for that device at that moment in time. To tie all this together, Ruckus uses what they refer to as a zone director. The zone director is a centralized controller that optimizes the wireless environment and provides troubleshooting through what we call visibility, where you can see one, full overlap of the coverage between access points, along with what's happening with the client device as it moves through the environment. All aspects of how the wireless environment is performing can be seen whether you're on-site or you can log in remotely through FlexMaster to see the same thing. This provides a single point of interface for faster and easier deployments, and with FlexMaster Remote Management allows you to not have to roll a truck to a particular site to see exactly what's going on. So overall, the Ruckus advantage is simply better wireless. BeamFlex provides higher signal and noise ratios. It's additive to chip-based technologies like beamforming or multi-user MIMO. BeamFlex Plus provides horizontal and vertical antenna arrays, which are optimal for mobile client devices, which is, let's face it, the majority of devices that are using wireless energy or Wi-Fi connectivity. The Zone Director provides centralized control, optimization, and management of the entire wireless network, while FlexMaster provides a single pane of glass for remote web-based monitoring and control of each Zone Director system. Overall, why Ruckus? Because it needs to work. All right, so we went through a lot of information very quickly, and that is the end of the presentation. Let's see what we have for questions. So Marley? Okay, we're going to start off with question 25. Can you briefly describe the implications of bandwidth on Cat cable, i.e. Cat 5 equals 100, Cat 6 equals 250, etc.? Well, Category 5 cable and Cat 6, either one of them, Cat 5 can carry gigabit connectivity. Well, 100 meg. Cat 5e will carry gigabit. The reality is 5 is going to carry about 350. But those are all full duplex communications. Wi-Fi is going to be half duplex. What we're finding is, even in most wireless connectivity, you're not approaching, even if you had a 4-antenna device right now at 160 megahertz channel width, you would approach 1.7 gig connectivity in a perfect world, which, again, in a perfect world would give you only 866 meg throughput. Realistically, you're probably only going to see about 500 or 600, so we're not yet at the point where we're eclipsing what you can do on your standard 5e or Cat 6 cable. Doesn't mean we can't. The standard's written to go up to 7 gig. So there is potentially a time down the road where you can have a particular device that could have higher throughput than what the particular Cat cable is capable of. But you need to take a lot of things into consideration there. Technically, if you really want to plan for that, you can run 2 Cats to the location. You could bond those together to provide a 2 gig pipeline. You could also, there's newer technologies coming out, which the N-base-T and gig-base-T alliances, where they'll have between 2.4 and 5 gig or 2.5 and 5 gig connectivity on a single cat. And then additionally, you have to understand what you're transmitting to. We rarely are connecting to anything wirelessly on the other end that are going to provide a gig of throughput. Let's face it, when you're downloading video from the internet, you're talking, even at high def, you're probably not going to exceed more than 20 meg most of the time. And let's just say you hit 150 or 200 meg on some big downloads. You're still not even coming close to what you would on the gig connectivity. So I think you're pretty much safe with a single or definitely dual cat for many years to come. Let's see, 38. How does Zigbee systems affect and to minimize the impact? Well, when you're talking about, that gets into non-Wi-Fi device interference. Broadcasting on 2.4 gig, yeah, there's a lot of things out there that do. The way that you work against it, there's lots of things you can do. One, every manufacturer of Zigbee devices, they will tell you what channels or what frequencies each of their channels broadcast on. When you compare those frequencies to your Wi-Fi frequencies, you can plan for Zigbee devices in a particular area to use frequencies that are not being used by your access point in that same area. If you're unsure of that, you can use spectrum analyzers to see what's being broadcast on what channels in a given environment, and then use Wi-Fi channels that are different than what is being used by the Zigbee devices. For example, with Ruckus and the Zone Director, I typically will turn an access point into a spectrum analyzer in the environment and then record the result of what I see in the environment to then be able to determine which would be the best channel to use based on all non-Wi-Fi interference that I can see. Let's see, 39, what's 39? Do you have a licensed software to make changes to remote location? I'm not sure I follow the question exactly. When you have a zone director has licenses to each of the number of access points that it's going to be communicating with, and then you can log in directly to that through port forwarding, or you can utilize FlexMaster. And FlexMaster, you have a one-time license that covers the lifetime of interactivity to that zone director, which is how we always did it. You can always contact us directly, and we can go into the details of that. How will AC power line adapters be used to place APs in locations without pulling cat wire affect the signal noise and overall throughput? Well, AC power line adapters, you're talking about a couple different things. Power line adapter, by definition, is by transmitting networking communication through power line. If what you're actually referring to is PoE injectors or just powering access points that are remote and then meshing to the rest of the network, that's something different. When utilizing access points, you want to, of course, use access points that will create a unified wireless environment, because there's a lot of things behind the scenes that change when you're just putting individual access points that aren't designed to be unified. To do this, some manufacturers tell you to just use repeaters that just plug into the wall. The problem with repeaters is they will decrease your speed by 50%. Remember, we talked Wi-Fi is half duplex. I talk, the repeater listens, then the repeater talks to the client device, and then it listens and then comes back. So you've got this extra hop, so it decreases it by 50%. Manufacturers like Ruckus and Eero, for example, utilize some proprietary ways of communicating between access points. So when you mesh their access points, meaning connect them to the wireless environment without having hardwired Ethernet, when you mesh their access point in, they communicate to each other in ways that don't decrease the throughput to the devices to the extent that a repeater will. You'll always have a little bit of decrease, but their proprietary technologies allow them to do it in a way that it's a very limited loss when you go from access point to access point, even in that meshed environment. Look at 43. How should I orient 3 antennas on a WAP? All 3 straight up or 1 on each plane? That depends on your given environment and how the access point is mounted. if your access point is mounted, let's say, on a desk, and you've got a flat residence and you're trying to get all of the coverage throughout that plane, then you're going to mount all three of them straight up, because that will provide, one, your donut-shaped coverage from each access point to go straight out, and what you're actually trying to do then is maximize on the multi-in, multi-out scenario, so you want the highest throughput, highest gain for each antenna at each point that it's communicating to its client device. If you're talking a multi-level structure, then you may want to turn one or more of those vertically. But again, that's going to change your donut-shaped pattern. That's why with Ruckus and its vertical and horizontal-based antennas, it's still focusing the antenna energy like a Yagi, so it cuts through the problems that you face with just a static dipole that you're trying to aim. It dynamically will focus the energy to each space and time and each point that it needs. All right. Was it 57? 47. What do we got here? What about constant? What is it? What about content latency instead of? I'm not sure I follow the question. Every network is going to deal with latency a little differently. It's all going to be based on not just the wireless connectivity, but how the network itself handles communication. If you've got a flat network where you've exceeded the number of devices that can communicate latency-free, then obviously switching to a multi-VLAN environment will help. But again, this is, there's a lot more things to just consider. You've got buffering within devices. You've got buffering on, off-site. Latency can happen, between your device and the access point, between the access point and the switch, between the switch and the core switch or router, between the router and, different internet sites. So the more, I guess, astute way of looking at it is trying to ascertain exactly where the latency is occurring, and then you can very easily resolve it. It's one of the big things that we have to do is understand which tools to use at which time to accurately resolve issues instead of just guessing at them. Let's see. How would you compare Luxil's managed wireless to Ruckus from a sales aspect? Why would you sell one over the other? What I try to do is not disparage or necessarily go, I don't like going head-to-head on a lot of things, because every application and every user can tailor something specifically to what they want. I will go down the path of, when you take Ruckus, for example, that was designed for enterprise-grade, city-wide, campus-wide deployments with high level of interaction and needing 100% uptime. You're taking true enterprise-grade hardware, and now you're bringing it down into the residential market to be able to provide the same stability that's demanded by an enterprise-grade situation. Luxil and a lot of the other consumer brands, what you're doing is taking consumer access points, which from an engineering and design aspect were designed to be standalone single access points, never covering more than 12 to 1,500 square feet, and then trying to make them work together utilizing a wireless controller. Additionally, the Ruckus BeamFlex and BeamFlex Plus technologies will absolutely outperform any consumer product substantially, and it'll outperform even Cisco and any of the other on the the enterprise grade. Ruckus is known to be the highest performing access points out there. Additionally, you've got to look at the number of clients that can simultaneously be trying to connect to your access point. Most consumer devices tend to fail at around 15 to 25, maybe 30 trying to connect. Others can handle up to 100, but we all know that you have a good dinner party in the backyard or a wedding, you can easily have 300, 400, 500 people out there, which means that your Sonos that you normally can communicate with no issue, your phone or iPad can't even connect to it now. So it's critical that you know a lot of those parameters when going against it. And me as a company, when I was doing it, we knew that Ruckus could always outperform and brought the level that we needed to have. 53. Is media prioritization useful? Is media prioritization useful? Things like this, I think, are application and job specific. I have always believed that in the KISS scenario, keep it simple. The more we tend to analyze and determine which data has to go where, we're using overhead in the system, and things like that can be very useful in specific circumstances. But from a general scenario, it's probably not needed. So I think without knowing what your project or installation is, my overall approach to really everything in the industry was to be able to say, we know that this can do this. Here's the general setting of parameters and different settings that we've found to be generically the most stable and give us the highest success from a standard deployment rate. And then if there's individual situations that arise on a given project, being able to specifically address those one by one, some of these tools are going to be able to help. What if we hide the SSID? Is it preventing from every device in the area trying to connect to it? It'll prevent from most devices, yes. It's still broadcasting, but it's not broadcasting visibly. But again, it depends on your access point. If a lot of access points can only handle one SSID. The access points that I was familiar with could handle multiple SSIDs, and even SSIDs that are just specific to single access points, even though it's a unified environment. So to answer the question, yes, if you hide the SSID, client devices will not, for the most part, know that it's there unless you've told them it's there. But be aware, sometimes for clients, it also makes it much more difficult. What kind of learning curve is there for Ruckus products? Well, it depends on what you're trying to do. The basics of the technology I talked about here today with BeamFlex, BeamFlex Plus, zone directors, things like that, those are all pretty straightforward. We as a company help educate our dealers in those and how to deploy zone directors, and then we also do custom configure them. The easy statement is here's the technology, this is how you go sell it. The longer answer is, as with anything in technology, the amount of time and energy you invest into your education and understanding will determine your rate of success with it. Most of our dealers, utilize our custom systems, which are pre-deployed, and I've got, 8 Cisco engineers on staff that are here to assist in any way, shape, or form throughout, that lifetime of that project. The dealers and people who want to dive into it, you can spend. I've spent myself hundreds of hours of education with Ruckus to go through and determine, proper settings, how they affect different things, what they're going to do, how to understand the technology. And then after that, it's getting out in the field and installing it over and over and over again. I've got hundreds of installations where we've done, and some of the most remarkable things I've learned throughout my years in the industry have been on specific installations where everything should have worked, and yet it wasn't. And by learning what we were able to do to overcome those situations provided a breadth of knowledge that I was never able to receive during, most, book and online education. All right, I think we're pretty much approaching the end of this. I will go through any of the questions that are here that I did not get to, and I will respond to each of you individually. Please feel free to reach out to me. I know that my email is on the previous slide. So if there is any information that I didn't cover that you would like some information on, and if you have asked a question that I haven't gotten to, I apologize. We tried to do the best we could to choose which ones were the most beneficial right now. But I will respond to each one of you individually over the next, shortly, hopefully within the next week and a half. Thank you all for attending, and I look forward to hearing from all of you.